Okay, try to recall that somehow we, in the balanced case, we were getting minus in the front, which was later on converted with the help of Hadamard gate into 1. Okay, so that was a balanced case, and the other case was constant. So because the phase kickback means phase kickback in the sense the behind person, the ancilla qubit is kicking its face onto the main qubit. Okay, so that's why this was a phase. So plus sign was changing into 1 minus, and that minus sign was making that plus sign into from 0 to 1. So that was the phase kickback operation. Okay, so in here as well, this is the same thing, and this is the Grover diffusion operator. So till now we understood that, till now this is the thing that we have already read in the Deutsch algorithm. We have done its mathematical representation as well, and Grover's diffusion operator. Now the main point is we can apply the Hadamard gates. How do we do this? Okay, earlier y's or f of x was there, that we knew that we can construct a unitary, we can construct an oracle out of it, and we can apply that unitary onto the circuit. Now we will go into here and we will see how to do it. But of course, in Deutsch algorithm, we only have seen the theoretical part. This unitary part we have not seen. We didn't see that how that unitary was working in implementation. So we will also go into that. So I've shown you the very basic size of the screen. Okay. Mirror.
Yes.
This I can go this much only. Okay. So this is just a write-up about the Grover's algorithm from the very starting, from the very morning. We are trying to see that kind of theory about it. So it's very nice that we got this Grover's algorithm from Love Grover, who was pioneer from India and from IIT Delhi. He did his BTech in electrical engineering from there. And of course, this algorithm, because search algorithm, and we have seen what is unstructured search. Unstructured search in the sense we have a data set which is randomly distributed in a space, you can say. Okay, and we have to figure out, we have to come up with a value which we are interested in. Okay, so that is, we are searching for some value in that unstructured database. Okay, so for any classical search algorithm, we would be using, in this case, we would be using any brute force algorithm, any classical algorithm. So for that, we would be requiring n number of computations. Of course, because if we are having 10 numbers in a database, and we are looking for one value into here, and if that particular value is at the very end, that means we would be requiring n number of computations. This is a very simple example, right? So let's say I am interested in, this is my database, this is unstructured. So I'm interested in 12, but I don't know where that 12 is. Okay, so that's why I'm looking for I'm going for some algorithm, any classical algorithm. I'm just asking, okay, I need 12 number out of this database. So it will just go into it. It is unstructured. It cannot use any kind of other, divide it into half and do that particular kind of search. So it has to go one by one. Okay, 0, no, there is no match, no match, no, yes. So in here I found it, but it took me order of n time. Okay, and now Grover claims that it can do the same search in order of root of n. Okay, so now let's see how it can do it. So okay, So let's start how to do this implementation. It's a little, I would say a little different from what we understood, whatever we are doing over here. So let's try to understand into a form of quantum. How do we do a programming in quantum? So first of all, we have to convert everything into 0 and 1. So we will not say, I would not say that I'm converting this 0 into 0 and 1, 3 into 1, 0. I'm not doing that. What I'm doing is, I'm thinking now, because I want to convert into a program. So think of this as some indexes which are randomly distributed over here. Of course, I would be requiring 3. Okay, of course I would be requiring 3. So let's say some of the, okay, these are the indexes. Okay, so I'm interested in 0, 1, 1. Okay, so this can be converted into a superposition form. Okay, so there would be some values, amplitudes corresponding to these. Okay, so I would say that I'll initially start with some equal superposition. Equal superposition, you know. Okay, so this is the basis state. That basis state can be 0, 0 or plus of 1, 0, 0. Yeah, of course. In the end, it would be sum of the amplitude over here corresponding to 0, 0 plus of 0, 0, 1, 0, 1, 0 and so on till 1, 1, 1. Okay. Now we have converted our classical problem into quantum. Now let's start. Understood till now? Okay. So let's start this. So this is what I have done over here.
The list need not be sorted. The list.
Yeah, list would not be sorted. We can say that list is not sorted, but it is in superposition form. Okay. So in here, if you see my text box over here, I have written that I have designed a circuit. I have created a quantum circuit with the help of quantum registers. I am using 3 number of bits over here. So 3 bits means 2 power n, 8 number of superposition state basis states, and I am applying Hadamard gate on each of these. So this is just a looping that I have done in order to create a superposition state, equal superposition state. So in the end, I get this particular wave function. Okay, clear? So now I have created a superposition state. Okay, so this is the representation. How do I create a equal superposition state? So I have created it. And if I run this particular, so of course I have here, this is the state vector representation, and for the probabilistic representation I have to measure it with the, so here I am using simulator to measure it. So this is the simulator. I just what I am doing is I am applying Hadamard gates over here on each of the qubit and then measuring each of the qubit and getting the counts at the end. So get count means that I am getting the probability. Okay, so this is the probabilistic view corresponding to each of the basis state. So okay, so I can create an equal superposition state. I can I can run it on any simulator and can create an almost equal superposition state. Now the point is oracle. How do I know that, how do I tell my oracle that I need to search, I need to look for this particular value? In classical, we can say, okay, this, I am giving some database, I need 12. Just let search for it and give me some value. Okay. Now here what I am doing is I have to tell that, okay, I need this particular value. This particular value I need. This particular index I can say. This particular index I need. So for this I have to somehow create my oracle in this way that I'm just telling that this particular value I need. So what I can do is I need to mark this state. Okay. In the Aniket must have told you I have to mark this state. So in order to mark this state, what I can do is, because I know that 111 is the unique state, with the help of 111 I can implement some of the other operations as well. I can do the C node with the help of 111 if I would be having 111, and other control operations I would, if I need, I can create it. Okay. So what I have to do, first of all, I have to convert my marked state or the state which I am interested in into the 111 form. Okay. So what I can do is simply just apply X gate wherever there is a 0 in my marked state. Okay. So I'll apply X over here, identity over here, and X over here. Simply, I can do it. So what here I have shown is, initially I'm just for telling you what I'm doing. So initially this was 111, okay, and I have just added minus in front of it to show you that after the X transformation, after this X transformation, I'm calling this as a X transformation, how this minus is switching. So if I apply X gate, if my state is 0, so this minus is moving to 0 because this 1 is also shifting to 0. Okay. So let's say I'm applying X gate on each of these qubits, and this minus I'm showing you just to tell you that this, whatever this state is changing after doing the X transformation. So if I apply X over here to both of these qubits, it will be converted into 1 1 simply. 1 0 would be converted into 0 1, 0 1 1 0, and 1 1 is going over there. Okay. So that means X transformation is working fine with me. So in this case, what will happen? So I told you earlier, if my marked state is, if any state I'm interested in is, if that state is 0 0 1, if I'm doing the X transformation only on the state where 0 is there, so that means that can be converted into 1 1 1. As you can see, there is no other state which is in 1 1 1 state right now. Okay. So that will help me somehow mark my state. Okay. But still it is not properly marked. Okay. So what I'll do now is, now the proper oracle function is coming in. So I need something. So what I am doing over here, so this is 0 0 0 and this is minus of X. So I need some ancilla over here so that after the X transformation on my interested state, I can get minus of 0 1. Because anyways, if I am asking the oracle that I am interested in this particular state, and after doing X transformation, I have converted this into 1 1 1, and I have done all the Grover search algorithm, and it at the end it is giving me 1 1 1. But according to me, I was not interested in 1 1 1. I was only interested in 0 1 0. Okay. So converting this into 1 1 1 form has somehow marked the state, but at the end I would be requiring 0 1 0 only. So for that case, I would be needing to do something else as well. So from the Dosh algorithm, I understand that I can do a phase kickback over there. So with the help of, if I would be having 1 1 1 in this case and minus is here, and if I do a C naught, 1 is here, 1 is here, and minus over here. If I do control C naught, at the end, what I'll get? The output would be minus of 1 1 1 minus. Okay. Now what I can do is, so this is the thing that can happen. You can do it on your notebook. Control X, you know. If both of the qubits would be 1, that this would be changed. And if this is changing, a phase from here, from 0 minus 1 is getting shifted to 0. So that means after doing the transformation, I would be requiring 0 minus 1, and this minus will go on in the front, in here. Okay, you can do the simple calculation of this. This is a phase kickback which is happening. So now what I have done, I have converted this 0 1 0 into 1 1 1. Okay, and now then after doing this, I have done the phase kickback, and now I have got this particular minus over here. Now what I can do, if I again do the X transformation in the similar way, I would be getting the state which I was interested in. Say I was interested in 0 1 1, I would be getting minus in front of 0 1. So in this case, at the end, what is happening over here, I am marking my 0 1 only. I am not marking any other state. I am only marking the 0 1. So this is why I have written over, this is why I have shown this, that first what I will do is, if I am interested in 0 1, I will do X transformation. With the help of X transformation, this will be converted into 1 1, and with the help of NCLA, at the end I would be getting this case after again after X transformation. We will understand it more clearly. So this is the operation that I am doing. Okay, X transformation, then N naught means C naught. If you would be having 2 qubits, then CC naught. If you would be having more than 2, then N naught, you can say. And then again X transformation, and you would be getting the answer. So let's see how it is going. So this was my initial state, and I have given that I was interested in 0 1 0. So with the help of that, I'll show you the program as well. This was my initial equal superposition state, and in this equal superposition state, I was interested in 0 1 0. I have done the X transformation, I have done N naught, and again X transformation. This is converted into minus of 0 1 0. So somehow I marked my state. Okay, now I have marked my state. Now my kind of oracle has marked the state. So oracle would be requiring, so in this case what is happening, in the very starting I have to tell the algorithm in which state I am interested in. I have told that I am interested in 0 1 0. So in the first step, what it will do, it will just mark that state. Okay, this is the state the person is interested in. Okay, now it has marked this state. So what was happening? So this, with the help of Hadamard gate, all those Hadamard gates, it is doing the equal superposition, and then X is applying, I am applying X gate on the NCLA, because initially everything is starting from 0. So I have to apply X gate to convert into 1. Where is, okay. I hope this is understandable. Okay, so this is the initial state I would be having. Okay, after doing Hadamard gate, after doing, if I am interested in 3 qubits, I have to do Hadamard on all those 3. Okay, first, second, and third. This is what I have done. Okay, now this, in the initial case, you would have seen that this was something I have written. Means the diagram was showing something like that. This was Hadamard gate, and there was this 1 and applying Hadamard gate on this. Deutsch algorithm, remember? So to make it this 0, because by default everything is starting with 0 in Qiskit, I have to apply X gate on this. It would be converted into 1, and then I'll apply Hadamard gate. Okay, so that it will be converted into minus. Okay, that you know. Okay, now, so I already told the oracle this entire program that I'm interested in 0 1 0. I've written over there, and I have called then called the Grover oracle function, to which I'll provide the mark state, I'll provide the quantum register, I'll provide the ancillas and all those things. So in this here, what it is doing, first it will apply Hadamard gate on the ancilla. So this Hadamard gate is getting applied first, and then it will apply C0 gates over here. Okay, so this is what Grover oracle is. Okay, this is what I'm calling Grover oracle. Another thing is also coming up. Another oracle is also coming up. Okay, so at this point we have understood Grover oracle. So that's why I have written over here, if the length of the mark state means if I am considering only the 3 qubit or only the 2 qubit, so in that case CCX can be applied. Otherwise I have to go to n number of C0 gates. Yes.
We are supplied only with the indexes. How can we know the required state that it is that particular state has?
Suppose you have to assume, because we are working with quantum computing. So these kind of algorithms are very fundamental algorithms. They only talked about that. Suppose you are having some quantum state, equal superposition of quantum state. The representation I have shown you to make you understand that this might be something happening over here. Okay, so suppose you know the index of the of your value. If suppose you have known the index, somehow some person told you, okay, you need 12 and it is stored at 111. Now go and check in the database where that is. But now the database in the RAM, if it is stored in the RAM, you can understand that if some space is getting free on that particular space, your computer will save another memory. Okay, so that is randomly stored. Index would not be there. Okay, so now just look for the index.
Marking is also done randomly.
Yeah. Okay, so now I have marked my state. Now, okay, so this part is completed. Till this part, till U of W, it is completed. Now we need a Grover diffusion operator. So this is the tricky one. So this does the amplitude amplification. Reflection, it does the reflection and then amplifies the amplitude. Okay, so for that case, you got the answer that you got curious in the morning session as well, because this is what we were doing. Here is somewhere your state is, and suppose this is your 0 and this is your mark state. Okay, this is what we were doing morning. So now this is just for representation, for your representation that you are doing everything in 2-dimensional space. So the same thing can be done in block sphere as well, or Hilbert space. If I would say Hilbert space, this is a high dimension space. So in Hilbert space as well, this is a Y and this is a Z. So I would say that this is my mark state and this is 0, and somewhere around here my state is, which is making an angle theta. That angle initially, of course, that would be unknown to me because I know only the state. Where it is getting stored in the Hilbert space, that I'm just to show you, to make you visualize what is happening, just to show you that there is some angle with the theta. Okay, with this. So instead of Y, we are considering 0 over here. Okay, so why now the next question was why we are doing the reflection. Okay, there is a simple explanation behind it. If you are, I am just writing in the form of quantum state only. Okay, take any list, 0.7, 0.2, 0.1, 0.4, say this. Now R is my average. Take the average of it, some average, some value over here. Okay, now whichever state you are interested in, take that state. Okay, take that state, put it in here and see that whichever state would be more far to average, that would be reflected more. Okay. Okay. So you can yourself see this example. Okay, you just try to work on it and see this example, that whichever state is closer to this particular thing, or I would say far away from this particular thing, that what particular state would be reflected more. Just a simple, take any example, you can do it. Okay, the same concept here we have taken, the same concept here to do the diffusion operator. So now, suppose this is my unitary. Which unitary? Diffusion operator unitary. This particular, the entire thing, this particular unitary. Okay, so I'm considering that as any UF. Now, if I just solve it, this would be this, simply. Okay, now I told you that this is average and this is your state. Okay, now this is average. Now how do you create an average state in quantum computing? Classically you can do it, just divide with the number of values you have and you would be having your average. Now how do you create it? In order to create it, what you can do is, you need some, first of all, equal superposition state. Suppose in this case, S is my equal superposition state I have created. Okay, if I am creating that equal superposition state, and let me just check. Okay, so now I have created equal superposition state. That equal superposition state I can, if I write in this form, if that equal superposition state, I have created some equal superposition state, and if I write that particular state in this form, that is, now this is the inner product. This inner product will give you one value. Okay, always the outer product would give you the matrix and inner product would give you the value. Okay, so what it means, this S of psi, this inner product, it means that, okay, okay, this S of psi, this means that whichever amplitude, whichever states are correlated, those will be left, those would be 1, otherwise everything would be 0. So if suppose, very simple example, if S is 0 0 plus 1 1 and psi is 0 0 plus 0 1 plus 1 0 plus 1 1. Okay, what we can do is 0 0 plus of 1 1, 0 0 plus 0 1 plus 1 0 plus 1 1. Now what is happening, which is equally related, this 0 is related with this 0, this would be 1, this 1 is related with this 1, this would be 1, everything else would be 0. This would be 0, this would be 0. Okay, so answer you would be getting 2 over here. So I am just considering 1 in front of it, there could be any number. Okay, so this is giving me some value. So that particular value, if I write in this form with this S, if I multiply that particular value with this S, you would get an average value. This is a simple mathematics. Okay, you would get an average value. Now what you have done, you have got this average value over here. The same way, you have got this average value over here. Okay, now everything is same as classical. Now, in order to create that particular thing, equal superposition state is just what you can do is equal superposition state. What we have created, we can create Hadamard, we can apply Hadamard on 0, 0. Okay, this is what we are coming up. So what we can do is over there, if we can apply Hadamard on 0, 0, any 0, 0 state, we would be getting equal superposition state. Okay. Now what I have to do, what I did, I used Dosh algorithm. I just applied simple Hadamard gates and that's it. So what is happening over here? I applied Hadamard gate. These are just the set of C0 gates. Okay. Now in here I'm applying Hadamard gates again, and then the state would be converted into some of the zeros forms. Okay. And now at the end, what I'll do, I'll apply Hadamard gate and then do the measurement. So let's see what is happening. This is the same thing. I'm just taking 2 qubits over here. I'm telling that this is my state that I would be interested in. This is the unitary initial Hadamard gate and X gate that we need to do. Okay, Grover oracle we applied Hadamard gates. Again, what we have to do? We have to do the Grover oracle. Again, we have to apply the Hadamard gate. This is the same thing. Okay, Hadamard gate. Here the Grover oracle would come. Again, the Hadamard gate. Just that. So what I would see. So this was my initial state. This was my initial state. I was interested in 1, 0. After doing Grover oracle, it is marking this state. And after doing this diffusion operators, I am only getting 1, 0 with 100% probability. Okay. The rest all are 0. So this is what searching is. I was looking for 1, 0. I have marked this state. I've got the 100% probability of 1, 0. Okay. Till this, everything is clear, I hope. Okay. So what is happening? So this is actual representation of amplitude amplification. So suppose this is the this is your amplitudes. Okay, corresponding to each of the basis state, and this is your average. If you flip your state around the average, only the state which is negative in this case would be flipped very high. Okay, so you can do this mathematically as well. Take any, I showed you the database you can take, put any negative value in that and say that you are only interested in that particular negative value. Just the simple calculation, you would see that that particular negative value will at the end would be having the highest value compared to all other positive value. So in this case, what we did, we just marked the state in which we are interested in negative. Just put that into your this diffusion operator. You would see that that negative state will only that negative state will be flipped higher, more compared to other. So okay, so this is just a basic representation what we did over here. Okay, so it is not always that you will get your answer in one go. Okay, suppose this is these are equal superposition. You have marked, that means it is going negative. Now you have to flip above the so that particular state only which you marked flipped to above the average. Okay, in one go you are getting this kind of answer. Okay, Now suppose if you do this operation the second time, if you do this operation again, you have to flip your state, and then everything you are doing again. Again the average would be somewhere down, and if you flip it again, yeah, your marked state would be the amplitude corresponding to the marked state would be very high, or the probabilities you can say. So now there is a stoppage point over there. So suppose after that point you you put your everything into Grover algorithm again. You did the calculation again. So what will happen? The average would flip somewhere down here. Now, except the state which we are interested in, all other state would go into negative. Now, what will happen? Again, if you do the Grover oracle in this case, except this state, every other probability will go high. So you have to stop at some point. Okay. So that point was the pi by 4 root of n, somewhere around here. So here n is your number of inputs you are interested in, and you just multiply with pi by 4, you would be getting approximately value that till what you have to go. So let's put everything all together and see the result. So I have done a equal superposition. I'm doing here for the 3 qubits. Okay. So okay, again the same thing. Okay, I have to check in which state I was interested in. Okay, 110. Okay, now I took the 110. 110, I have not shown the in between steps over here. 110 I am interested in. Okay, I marked the state, I have done everything. After Grover iteration number 1, I would be getting this somewhere around 110, I would be getting 0.88 probability, 0.1717. Every other state is in 0.17 except this one. If I'll go one more iteration, I would be getting 97% probability of this in positive now, and negative everything else. Now if I stop over there, that is very good. Otherwise, everything will fed up. Okay, if I put this in any simulator, this is what my result would look like. I was interested in 110 and I told you Qiskit does this 110. Okay, you have to go just opposite. Okay, so 110 is 94% and every other is 0. So this was the implementation. I'll share the file with you because just going through the program was not important. How it was implemented in the program, because what you have done in theory class, what you have seen in theory class, this implementation is completely different from that. Okay, so if you have any questions, I think I've completed in very less time. Okay, any questions?
Calculation is 97%. But it is showing
94%. Yeah, simulate. I have just run it. That was just my wave function. I have just taken the wave function. Okay, somewhere it will vary. If you are running it on simulator, it will vary a little. Okay. This one? Oh, okay. Grover diffusion operator, this one, and Oracle, this diffusion operator. This is 0. This is 0. This is complete diffusion part. This is diffusion operator. If you implement it, you just need Hadamard gates only. Okay. Yeah, this one just C-node gates. C-node gates. If you are taking 2 qubits in here, if you are taking 3 qubits, then C-node, and if you are taking n qubit, then n-node. Okay, I'll show you. These are your starting points. This is your ancilla. You will apply Hadamard gate, Hadamard gate, Hadamard gate, and in the unitary part, this is your unitary part. Okay. In composer, if I'm applying this gate, it will look like this.
Suppose if we want to design for our application, what kind of changes we will do?
That depends on your problem.
Not able to understand.
Okay. So, first of all, these quantum algorithms are not like machine learning algorithms. These fundamental quantum algorithm I'm talking about. Okay, I'm not talking about other algorithms. So I'm talking about these fundamental quantum algorithms. These are designed in this way. Okay, you can directly take this or take some of the functionality. Like I told you, this unitary came from Deutsch algorithm. Okay, so this Grover used that Deutsch algorithm as it is in here. Okay, he saw that, okay, this is what it can use, this can use. Okay, so he implemented. Okay, so now you have to see what functionality you can use. If you want to use this entire Grover's algorithm, you can use it. Okay, so Grover's algorithm is used for the amplitude amplification as well. Okay, so amplitude amplification, if you have some kind of problem where you are just trying to amplify some of the values, suppose I'll tell you the machine learning example. You would be having number of features. Okay, in those number of features, you are only interested in 2 features. Okay, which you are most interested, and you are thinking that according to you, those features can give you the highest accuracy. So what you can do with the help of Grover's algorithm, you can amplify those features as you do the weight corrections. Okay, you just apply amplitude amplification over there, increase those values for those features only, and rest will go to 0. It is a kind of classical implementation, a quantum implementation of diffusion part, but which particular features you would need to amplify, that you would be requiring. In that case, you would be requiring this. Yeah. Okay. Any other questions? Any kind of?
I did a mistake. There was control swap gate, which I showed. But I said by mistake. This is the CG not gate, and when I showed the swap gate, it was control swap. So it was like control and cross.
Cross operator. So control swap gate. If we are talking about control, some of the qubit is control and other thing is getting swapped. Okay. Or you can say, in this case, control swap gate means this. If this is 1, then only these 2 will be swapped. Okay, so this is control swap.
Abstraction that we use get amplification function.
I told you, this is the way you can use it. Feature extraction also you can use it. For feature extraction also, you have to think in that form where to use and how to use. Okay. The entire algorithm is front of you. I told you it can do the amplitude amplification. I told you an example that you can do in feature selection as well. So feature selection, if you can use it, then of course you can use in feature extraction. You have to think in that form. Any other question? Okay then. Still 10 minutes, I think. 40.
Tea is already available.
No, it's okay. That is okay. I'm just asking. I've completed it 10-15 minutes before.
So just because we have some time, someone asked me that how do you design an oracle for growers for our specific problem? So that's a great question, ma'am. So my answer simply is you have to break down for your own problem and do the R&D because right now it's a very open problem. Whatever we could give from say scratch to some example that I discussed, or even the implementation which Diksha showed, and even the intuition which Gopika gave, this is what we get from textbook, but I will still only tell you, my suggestion would be that any problem that you're trying to define, how do you design means you have to play with gates. What will happen is, like, we are all classical people now trying to understand quantum, except few physicists already in the group. But what I'm trying to say is that if you want to design any oracle, you have to just all the gates are there. No, there's the Y gate, Z gate, there is control Z gate. So you have to play around with this. How we are babies, we are playing with toys. So you have to play around with the gates and see how that gates do any operation. Then you can indigenously, on your own, maybe come up with some solution. So even the example which I showed you was not something which you can intuitively, you cannot come up with it. You have to do the maths. Basically, you have to apply pen and paper and see what would take place. And yes, there are very important gates. So what I would again suggest is there is this C0 gate, CC0 gate, control. Yeah. Then there was the swap gate. So these gate operations are something which you have to keep familiarizing yourself with. So if you ask me for an example, I think we already stretched ourselves by giving that. My God. Okay. All good? No, I won't. Because at least people here could hear, no? So my only suggestion would be that we gave you as much, practical example as we could, and also showed implementation. Only idea now is to apply yourself. So the question you're asking, probably I will come back to you and ask after 1 year, what was the solution for the problem you took? So you have to come up with a problem which you could solve and then propose a solution maybe. That's the only thing. If any other questions, we are always there outside the class timing also, but okay. Thank you so much. We'll take break now. Thank you.
Dr. Devendra Mishra, quantum hardware lead, quantum AI global. He has done his PhD from Indian Institute of Technology, Hyderabad in quantum optics and quantum information. He has done MSc in quantum physics at Indian Institute of Technology, Hyderabad. He worked as technology head of quantum hardware and as technical lead quantum hardware in QLab Software India Private Limited. He also worked as head of quantum hardware, quantum AI global, and he is currently working as quantum hardware lead at quantum AI global. Let us all welcome him.
Thank you.
Already my colleagues, they have discussed a lot of quantum computing, and most of the information's already been discussed. So as they introduced me, my background is physics, and I'm working in quantum communication. And my perspective of quantum will be on a communication side. So my topic is to understand the quantum entanglement, Bell states, and okay, it will work. Yeah. Is it? Hello. Okay. ఇక్కడేనా లూజ్ కనెక్షన్ అక్కడ లూజ్ కనెక్షన్ అనుకుంటా అక్కడ మనం నొక్కాం కదా 2 minutes. Okay, so sorry for the technical issues. And okay, all right. So my topic is quantum entanglement, Bell state preparation, and quantum storage. So we'll start understanding these things and a very fundamental physics point of view. So we'll start with how to understand what entanglement is on a very fundamental perspective. So this will be very abstract kind of discussion. So I ask you, all of you, to engage in such discussion, and you can ask questions anytime, and we'll keep it discussion mode. Okay, so I will not go very deep into like all of my colleague, but we'll be talking much details. So the objective will be to understand entanglement principle on a very foundational perspective of quantum mechanics, and demonstrate Bell state preparation methods, analyzing quantum storage mechanism, and apply the concept of quantum computing and communication. So that will be the objective. So I will start with a very fundamental question that has been like in the discussions since so long, and it has been a huge debate between the scientific community, between Niels Bohr, one of the founding father of quantum mechanics, and Albert Einstein. He was also one of the founding father of quantum mechanics. So in the description of quantum mechanics, when it was evolving, or the postulate has been given, so Einstein has some issues. So the classical mechanics, the way it has been evolved, so there was a concept of locality. The locality concept is, if something is happening at one place and something is happening at a different place, so some space like things are happening, 2 different places, 2 different coordinates in a space, so they cannot immediately connected with each other. It means information cannot travel faster than speed of light. In a very simple term, that's the locality. Because if information can travel faster than speed of light, 2 events can be correlated simultaneously at 2 different places. For example, if one event is happening in this galaxy, Milky Way, and some event is happening in Andromeda, the neighbor galaxy, so both 2 events cannot be simultaneously correlated. That's the meaning of locality. And the realism is the nature we perceive is real, means it doesn't depend on whether we are observing it or not. So if, let's say, there is a tree which fell down in a forest, it fell down, whether somebody has seen or not, it happened. So that's the realism, means our nature is basically real. So that's two concepts, and both were violated by the concepts and postulates of quantum mechanics. And then Einstein has serious issues, and he has published a paper with one of two colleagues. It's called, I hope you can see, Einstein, Rosen and Polosky. So there is paper EPR paradox or EPR paper. So the title was, can quantum mechanical descriptions of physical reality be considered complete? A question mark. So Einstein point was, quantum mechanics is giving a good results, correct results, but it may be either not completed or wrong the way it has been given. So as I will going to explain later, means how they have violated the two principle, which is called locality and realism, and Einstein called it spooky action at a distance, and that's the huge debate, uproar happened at that time. And with the time, it has been tested experimentally by John Bell and Bohm. So these people, they have worked on the experimental perspective of that, which is something called entanglement. So we have studied entanglement a lot. Now we're going to see how entanglement can be generated and how it breaks the principles of our all nature. And all our fundamental particles are quantum, and we all made of by those fundamental particles. So in a way, we all are quantum, but their average effect is being seen in the day-to-day life. So they can be considered as a classical, and a classical mechanics, Newtonian mechanics can explain that. But in reality, nature is not the way we perceive. So in Advaita Vedanta philosophy, something is called Brahma Satya Jagat Mithya. So Einstein came and said something is fishy here, and said that quantum mechanics can be wrong, or it's not correct or incomplete or wrong, because we are going to a very thing which is not explainable, spooky action at a distance, something called entanglement. So after experiments being done, and by the effort of John Bell and Bohm, they have proved that Einstein was wrong and quantum mechanics was correct, and our existence is not real, right? So that was, and Nobel Prize was even awarded. So in 2022, Nobel Prize was awarded of, so these three gentlemen, they have fixed some experimental loopholes in Bell experiment, and something they did called quantum teleportation, and they got awarded Nobel Prize in 2022. So how crazy it is, you can just think about it. So that motivates us to understand what quantum is, what quantum entanglement is, and it feels like sci-fi. But when you started doing the mathematics, then you came to know how it is. So you cannot understand it completely, but you can do math. Math is strictly complete, and doing math you will get all the results, but you will try to understand how it is happening. It's difficult. So that's the more or less understanding of quantum mechanics which I have, but I don't understand, nobody understands this. So that's the way it has been told. Shut up and calculate. I was discussing afternoon. Okay, so that is the quantum mechanics, gentlemen and ladies. So let's start deep dive into the subject. So first I will start my talk with the very fundamentals. Already my colleagues have discussed a lot, but still I will give some of the aspect, and then we'll deep dive into how entanglement is created and how experimentally you can verify what is the Bell pairs, and then how to store and where it comes what I work, I means my company, what we work, what we develop, and why this is important for the scientific community and even humanity. So that will be the summary of my talk. So first is, so we'll go with the some, yeah. What happened? Can you just make it full screen? Yeah. So concept of qubit. So what's the qubit? So all we know, like in all of you from computer science, more or less computer science department, we know bits, like zeros and ones. Qubits are a specific entity. So from physics perspective, I would say a fundamental particle which property have like 0 or 1 simultaneously or in a superposition state. So there is a probability of getting 0 or 1. So that's the qubit. So a photon, an electron, ion, anything very fundamental particle that can act as a qubit. So in a quantum computer, superconducting ion or trapped ion or something like that, they can act as a qubit and they can be in the state of superposition. So you can see here, and it's a Dirac notation of that qubit, and it can be written like this: alpha 0 and beta 1, ket 0 and ket 1, and the probability is alpha mod alpha square and mod beta square. That is total probability of 0 and 1, which is 1. So that's the notation of that, and this is a single qubit notation. We can come with the 2 qubit notation as well, and already we have discussed a lot the block sphere, how block sphere works. So I will not deep dive into it, I'll just show it. So this is a single qubit representation of a block sphere, and a qubit can be in the superposition of single state. It can be 0 or 1, up spin or down spin, horizontal polarization or vertical polarization. So in the perspective of the entity or the qubit we are talking, a qubit can be defined either 1 0 or horizontal polarized, vertical polarized, up spin or down spin. So these are the mathematical representations of a single qubit. Now we'll see, so single qubit is one representation called state vector representation that we discussed in the previous slide. But understanding quantum and multi-qubit system, a density matrix formalism is very much required. Without it, we cannot get the full mathematical grasp of it. So you see, so this is the state vector of a 2 qubit. So 0 and 1 earlier, those were the basis of the Hilbert space. And any single qubit can be represented by using the previous one, like 0 and 1 by root 2. And this is the 2 qubit representation, 0 0 and 1 1 by root 2. And so this 0 0 and 1 1, these are the computational basis of a 2 qubit state. You can write like this. So there is something called pure state. So all the state vectors that we have seen are the pure state. So some state vector can be written in form of state vector, they are called pure state. And some mixed state, they cannot be written in terms of pure state vector. So for understanding the mixed state, you have to define a density matrix. So density matrix is rho. Rho is, you can say, outer product of 2 ket vectors. So it will be a matrix, and so you can see for this example, this is the density matrix of rho. It's fine like this. So now you can separate this. This is the density matrix of a state vector or pure state. So you can separate it, and it's called separable state, where a 2 qubit state can be written in terms of single qubit. That's called separable. And some states, they cannot be written in a separate form of single qubit states. So they are inherently mixed. So that's called entangled. So before quantum, entangled word was there even before quantum, entangled state, and I will come to that. Those are called Bell state, so which are correlated and they are maximally entangled. So so mixed states are, so how to represent them? a pure state vector will touch the surface of the Bloch sphere in a Quiskit representation. A mixed state won't be. So it will be shorter, the state vector will be shorter, so it won't touch. So the way you can visualize a mixed state as well. So what I have explained, the state vector, 2 qubit notations, separable states and non-separable states, and something called maximally correlated state, which is called entanglement state. So now I will go into that. And something is called fidelity. There is a term fidelity, which basically works with the density matrix of it. So if you have an initial state psi and its density matrix is rho, and if it is a pure state, the value will come the inner product like expectation value of rho by using that Kate vector. So it will come 1 for in case of pure state, and a mixed state it will be less than 1. Okay, so that's the fidelity part, and it's defined like this. So how to calculate fidelity? I have given one more example. So for example, if you have a state 0 0, it's a 2 qubit state, and there is a density matrix is this, and if you calculate fidelity, it came to 0.9801. It's not 1. So after calculation you got 0.981. so it's not a pure state, it's a mixed state. Okay, and it's because of fidelity is less than 1. So that's some interpretation, mathematical requirement. So now I will come to the entanglement and the Bell. So what is happening? Can you just, yeah, sorry for that. So these are the maximally entangled, maximally correlated states, mathematically 2 qubit state. So here you see 0 0 1 1 by root 2, and 0 0 minus 1 1 by root 2, 0 1 1 0 by root 2, and so on. So you cannot write a single state vector notation of these states because they are maximally correlated states, and a single qubit cannot be written in form of that. So they are non-separable, they cannot be separated. And that's, so it means if a particle is measured either I have a one part of particle, and let's say sir has another part of particles, and if I measure it, I got 0, he will definitely get 0, and if I will get 1, immediately he will get 1. So assume that I have that particle with me, and I have sent other particle with different universe, different galaxy, and still this is valid. So if I'll get 1, so it's not fixed whether I will get 0 or 1, but if I'll get 1, definitely other one will get 1, and if I'll get 0, definitely other one will get 0. So see, the results are correlated and it's not decided. So how the information is getting it's traveling, information is going faster than speed of light, and it's breaking the locality principle. So that's the entanglement. And so that was the main point of Einstein, that it cannot break the speed of light principle, and it's breaking clearly. So this is how you create an entanglement. You start with a 0 0 qubit, you apply an Hadamard gate and a control CNOT gate, and you will get these pairs, and this is something called Bell state measurement. Once you will do, you will know what is the Bell state, either psi plus, psi minus, phi plus, or phi minus. So these are the different states you can create into Qiskit, and you can find the entangled state. So there is something called localized entangled state and something called non-local. So let's say you created entanglement inside a quantum computer. It's located very single place. But if I created two photon which are entangled and I'm sending it different places, so they are non-local. They created at one place, but they are at different places. So that's photonic qubits. And the previous one was, let's say, superconducting qubits. So that's the difference between them. So now I will come to the photonic entanglements, and one more important part. something is called Bell basis. So already my colleagues have explained you the Hilbert space. There is basis, something called basis, and you can write any state vector or any qubit state in terms of those bases. So we have here a computational basis for 2 qubit for single qubit computer, and it looks like something like this. So you apply a CNOT gate and one more Hadamard gate, and then X and Z gate operator, and you will get a Bell state measurement and you can get some results. So that's how it does in quantum computation. Now I will jump into the communication, how a photonic qubit is created, and how we can see in an experimental perspective of an entanglement. So as I said, 0011, all Bell pairs can be written in terms of, so photons have a fundamental property is called polarization. It can be either horizontal or vertical or in superposition of that, and it can be easily manipulated by using a wave plate. Something is called wave plate, half wave plate, quarter wave plate or something. By using the combination of that, you can manipulate those qubits. So that's the beauty of photonic qubits. So what will be the Bell pairs in terms of photonics polarization? That these are that HHVV, HH minus VV, HVVH, HV minus VH. So these are the Bell pairs in terms of photonic qubits. So how to generate them? So what I have explained, single qubit notation, 2 qubit notation, and understanding of the Bell pair. And previously I was explaining the locality and realism, how they got broke inside the quantum mechanics. So now I will explain how to create that entanglement or Bell pair by using the experiments we have conducted and some devices. So yeah, so let's discuss a very quick theory of entanglement generation. So something called SPDC, spontaneous parametric down conversion, where we use a non-linear crystal, and a non-linear crystal will be pumped by a very high power laser, and there will be 2 photons, signal and idler, they will come out. So those 2 photons, they are entangled, and we can use it for Bell state measurement or something like that. So how can I go back? This has yeah. So these are the crystal. So let's say there is a non-linear crystal, and you use some pump light, and you get a different frequency out of it. So the frequency will be same, so input frequency and output frequency. So the pump frequency will be equal to the signal and idler frequency. So omega p equal to omega s and omega I, signal and idler, and at the same time the moment. So it's a energy conservation and momentum conservation. So these 2 principles will always be same. It's not violated. So so this is something called phase matching condition. So input, what will be the phase of pump, that will be equal to the phase of signal and idler. So this is something called phase matching condition, and this signal and idler, these 2 photons are entangled basically. And there will be a temporal walk off and spatial and transverse walk off. So from the crystal, so you know light travels in a medium, and based on the refractive index of the medium, it acts differently. So let's say if it travels from air, it will be faster. If it travels from water or some other medium, it will be slower. So same way, different light and wavelength has feels a different refractive index. So here the signal and idler, they will feel different refractive index inside a crystal, the non-linear crystal, and they will create different speed. So because of that, they will create some sort of walk off when you will generate. So you will compensate them experimentally and you will get two entangled photons. So how they will come out? So let's say I'm talking about a BBO crystal, and BBO crystal, and BBO crystal will be pumped by very high power laser. So laser will be pumped and then you will get signal and idler. So how they will come out? It will be some kind of conical section. So it will come like a cones, and when the cones are coinciding, you will get entangled photon from that coincident sections. So horizontal and vertical both will be there. So these will be the representation of experimental representation of a crystal and how this entanglement is getting generated. So there are multiple schemes are possible. So you can generate a single crystal scheme or crossed crystal scheme or something called parallel crystal scheme, Sagnac scheme, folded sandwich. So there are different possible experimental way to generate an entanglement. Based on the nonlinear crystal, you can do that, and these will be these are the reference where all the details has been given. So these are the way how you will generate entangled photon. And so now it comes the interesting part, the Bell test. What John Bell did in the experimental lab at CERN when he was at sabbatical, and how did he test the Bell test and how he proved Einstein wrong. So this is the Bell test, very famous Bell test, and it's called CHSH inequality, the modified form of Bell. So I explained entangled photon, I explained polarization, and I explained the wave plates. By using them, you can manipulate. So how we will measure entanglement? We will keep a photodetector in front of the light which is coming. So that light can be measured by using a photodetector and a wave plate. So quarter wave plate, half wave plate, there will be certain angles. By using different angles, we will choose which basis we are going to measure. So these are the values E alpha beta, E alpha prime beta, E alpha beta prime, and E alpha prime beta prime. These are the different angles of the wave plate using at Alice and Bob. The two parts are two entangled sections, and by these experimentally measurable quantities, these are the experimentally measurable quantities, and these are the number, it's called S value. So Einstein, when he proposed the paper, EPR paper, and when he claimed quantum mechanics is incomplete and we are getting a weird conclusion out of it, he suggested that the information, so when I have explained that 0 and 0 are same at the same time, or 1 and 1 are the same at the same time, so he proposed there will be hidden variable in between. They will govern when the information will go, and it's even the speed of light is not getting violated. So one very famous example, that let's say you have a pair of shoes like left leg and right leg, and you separated them at a time, and one person took your left leg shoe and one person right leg shoe, and when you open the box you find left leg and right leg, but next time as well you find a right leg and then left leg opposite. So Einstein proposed in a quantum case there are some hidden variables, they are working at it and they are proving this thing correctly, and still speed of light is not violated. So John Bell devised this experiment and set the criteria. If there are hidden variable working in this way, then this value of this experimental measurable quantities, sum of the S value, it will be either equal to 2 or less than 2. So this is very long proof, mathematical proof, and he came up with this inequality. So if the S value will be less than 2, then Einstein theory will work, there are hidden variables, and there are possible hidden variables, and quantum theory is wrong. The entanglement description is wrong. If this violates, it means Einstein is wrong, there is no hidden variable, and quantum mechanics interpretation is correct. So that was the experiment designed by John Bell, and they did experiment, they conducted, even that same experiment we conducted on daily basis in our lab, the famous John Bell experiment. So after getting that, we calculated the S value and we got more than 2. John Bell got in his time more than 2, and that was the violation of Bell's inequality and proof that quantum mechanics is correct and Einstein was wrong. And whole thing, the localism and realism and locality, that is also violated at quantum level. So that's the famous Bell state experiment. So any questions or any doubts so far? If you have any question, you can ask, and then I will move to the next section. So very quick recap, what I have explained, the basic postulates of physics, locality and realism, and description of single qubit and 2 qubit, a Bell state, a quantum entangled state, and how they can be generated, how they can be tested, and the result which proves that quantum mechanics is correct, entanglement is true. So far any questions?
Entangled photons are in the laser, right?
Yeah, the pump is from laser, but there are a non-linear crystal I was explaining previous slide. So due to the non-linear effect, it creates 2 photons which are correlated, are entangled, and they can be sent 2 places and then measured. Yes. Yeah, correct.
Light consists of so many such photons.
Unentangled photon, they have trillions of photons, but by applying that non-linear medium, entanglement can be created. So that is the power of non-linear crystal. So if you have an ordinary laser, you will not get any entangled light out of it until you use a certain medium which is non-linear. So that's the source of entanglement. We called EPS, entangled photon source. Ordinary conditions, we do it on daily basis. We create a lot of Bell pair, we do Bell state measurements and everything on a daily basis. And even we have created entangled source for academic exercise as well, which we call it entangled photon source, QKD, EPS QKD for academia. So for you people to teaching kids and lots of researchers and professors the physics of it, and do by your hands to get this famous and groundbreaking things. So that's what we did in our company. So this is one of the points. So any other questions? Shall I move to next? So yeah, Bell violation done, as I explained. So Einstein was wrong and Bell inequality violates. So that was my whole point. So you will get value greater than, so there is an upper bound of S which is 2 root 2. So that value cannot exceeds from the 2 root 2, and the lower bound is 2. So if S value will come 2 or less than that, the process is classical. If it value comes greater than that and like beyond from 2 to 2 root 2, it's quantum. That's the test, Bell test of anything which is quantum. So these are our experimental, our EPS QKD. So you can do QKD. My colleague Riktim, he might have explained this setup to you. And these are the BBO crystal, and these are the laser. It's a 405 nanometer laser. And by using a half wave plate, we are pumping the BBO crystal, and we are getting these 2 photons, signal and idler, at 2 places. And there are 2 detectors. By using those 2 detectors, we are conducting the Bell state measurement circuit and Bell state measurement experiment, and by using single photon detection system, we calculate the S value, and by using S value we show that Bell violation and Bell inequality violation, and we show that we have entanglement pairs. So what are the usage of them? So as I explained, entanglement is very important entity, and by using it you can do certain teleportation of quantum state, not teleportation of humans, but teleportation of quantum states. So that's the application, and you can use something called QKD. So we all know every day, daily basis, this system got hacked, that system got hacked. Hacking, even you people teach ethical hacking, right? So so this is classical computer science and classical communication. People can hack, but the new information technology is evolving, which is quantum communication or quantum key distribution. Even a strongest computer in the world, a quantum computer, they cannot hack that communication, which is called quantum communication. So when you use quantum qubits or entangled qubits to store, so to share information between two parties. So assume we have an entangled pair, and one part with me and one part with someone else, and I'm communicating by using them. So this kind of communication cannot be hacked by anyone. By any sort of technology, it cannot be hacked. So unhackable technology is getting developed. So something is called QKD, where between two parties we share keys. So zeros and ones and strings of keys in a very secure manner, which is called quantum key distribution. And key ingredient of that quantum key distribution is EPS, entangled photon source. So you have entangled pair and you can do a QKD. So in our lab, we do that as well. So we create qubits, entangled qubits, and we share between two parties. Of course, both parties at the same place, and we share keys between them. And we calculate how secure they are, what will be the qubit bit error rate, all those sort of things. So these are the results. So as I was explaining, the S value should be greater than 2. So what is this value? Can you read? What is this value? Yes. So this is the violated value of S. So it means our setup is truly quantum and we have a true quantum entanglements, right? And then these are the qubit error rate and all kind of photon anti-bunching and all kind of results. These results prove whether those photons are truly quantum or not, and entanglement is truly quantum or not. So these are the results that we have, and even QKD results as well. So what will be the qubit error rate and key rate? These are the results of our setup. So a good news for you guys, because we have made this device already and we are selling this to academic institutions. So like IIT Madras, they are using our quantum memory products, and few more academic institutions, they are using our quantum products. So you people as well can take advantage of it. So now I will discuss something called, so what I discussed is at one place entanglement is created. So this is something called non-local entanglement generation, where two independent systems or ensembles can be entangled. So there is one place is one ensemble, it's nothing but atomic system, and there is another atomic system at two other place, and by using some kind of laser excitation at this place, I'm getting some Raman excitation, and I do a Bell state measurement between them, and this ensemble and this ensemble get entangled. So the way we do a quantum repeater, so I think Ritim already explained quantum repeater and entanglement swapping. So this is also one key ingredient where we can generate a very long distance quantum network or even quantum internet. So that's the amazing concept and crazy. It can so this is so futuristic. It can do unhackable communication between intercontinental distance. So main goal of our work in a company to develop, so I am leading the group where we are working on quantum hardware. We develop these devices, the EPS, quantum memory, I am going to come. So these devices, the goal is to develop such infrastructure, such communication system which goes to quantum networks or quantum internet. So that's the goal of us. So this is one of the backbone, quantum repeater thing, that will be a backbone of a futuristic quantum internet. So now I will go to the something called entanglement swapping. So now you created an entanglement, right? Now what you will do next? So in practical, so in theory it's very good, it's very nice to hear that one entanglement I have in one galaxy, another entanglement in another galaxy, but practically it won't work. So we create entanglement with 795 nanometer and it dies after few meters or few kilometers because of the atmosphere. There are air in the atmosphere and they absorb the photon. Or if you will send it through optical fiber, it has standard loss. So there are photons, a single photon level, they get absorbed. So how you will generate a long distance entanglement? This was the problem. And entanglement, unlike classical scenario, so you classically, how do you network? You amplify the signal. One signal you created, you amplify. And then you created towers in between and you all do long communication. But quantum signals cannot be amplified because no cloning theorem, you cannot copy. That's why it's secure. So you cannot copy a quantum signal. So what you will do? So this is something called entanglement swapping, where by using some devices you can store your entanglement. So which is called quantum memory. I will come to that. So you have to store your entanglement and then you have to swap a common part. So there are 3 parties and 2 entanglement. Entanglement 1 shared between A and B, and entanglement other one 2 shared between B and C. So at B, one part of entanglement and other part of entanglement, and I just explained a Bell state measurement. So you conduct a Bell state measurement here and then A and C will be entangled. This is called entanglement swapping. So here let's say 1 kilometer distance and here 1 more kilometer. So now you got an entanglement of 2 kilometer. Earlier you have 1 kilometer 2 entanglement, now you got 1 entanglement of 2 kilometer. Imagine this is 100 kilometer, you will get a 200 kilometer. So similarly, if you will have a multiple entanglement and multiple such entanglement swapping, you can create a quantum network out of it, which leads to a quantum internet. So this is called quantum repeater. That is a major part of my research. So that's the entanglement swapping. Any questions here? Because this is very tricky. People get often confused in this one. So any question as of now in entanglement swapping? No? So next thing is quantum teleportation. As I explained, in teleportation we can teleport with present understanding in different places, a quantum memory. You got a state and you did a Bell state measurement between that state and that entanglement, and the results you got, that results you send with a classical channel to other party, and now that without their connection the other party will have the same quantum information. So this is something called teleportation. So it's not the same particle. That particle died when they did a Bell state measurement. That particle died at one place only, but it had that quantum information psi, ket psi, that got traveled to another without even connection. So that's something called teleportation and quantum teleportation. So that's the difference. People often get confused that something got traveled out, right? And one very tricky thing, that you will not get that information until a classical information is given. So the confusion is, information traveled faster than the speed of light. Yes, it did, but you will not get any useful information out of it until you will send a classical message. So it's same like I am in this galaxy and you are in another galaxy and we did entanglement swapping. and immediately information went. But you will not know until I will send a signal here. Until we will talk over a phone, you will not get the useful signal out of it. So you see, signal is traveled faster than light, but useful signal you are not getting out of it. So still, speed of light violation is not being done. Still we respect Einstein. Physics respect Einstein. It doesn't break. Yes. So still we didn't break the principle of speed of light. Information is not, so useful information we didn't get faster than the speed of light, but quantum information went already. So quantum break that principle, but we will not get anything out of it faster than the speed of light. So that's misconception usually people have, that okay, quantum can do faster than speed of light. Yes, they do, but useful thing you will not get out of it until a classical information get communicated, and classical information is bound to follow a speed of light principle. So that's the explanation of quantum teleportation. Any doubt into this? Yes, it's been tested. It happened, but you have to extract out of it. So let's say I have shared that information due to the teleportation, but two party, let's say I have shared to you, but when you will able to know, so experimentally what is happening, I did Bell state measurement, I get some results, which is, let's say I did measurement, I got horizontal and vertical, these two results I got, and until I will call you and tell you ki measure it in horizontal waveplate or vertical waveplate, till now you will not get any information. So I have communicated you, right? I have told you use horizontal waveplate to measure. You have a part of entanglement, but until I told you, you will not get out of it. If you will randomly measure, information will be lost. So you will get a useful information by the speed of light only. You are getting the difference, right? So this is the quantum teleportation. Any questions here? Now I will move to next. Yeah, please.
Then where is the concept of entanglement?
Sorry?
Then where is the concept of entanglement?
So
Classical channel is coming.
So it's entanglement is there, and by using the entanglement only that data was transferred. So let's say you are here and I'm here, and we are 10,000 distance apart, and you have one part of entanglement and I have one part of entanglement. Because of entanglement only teleportation happened, and something traveled faster than speed of light. It happened, but useful information you will get only within the range of speed of light. So without entanglement, teleportation is not possible, even anyway. So that's the requirement of entanglement.
Done experimentation for this also.
Teleportation, it's been done. The Nobel Prize in 2022 is been given for teleportation only. We have done till entanglement. We are working on it. So clear?
Information we need that.
Exactly. But information traveled already. But to get you understand out of it, you need to know the information. Clear?
Information we are measuring. Finally, we are measuring from the surface.
Huh.
Is it like if I have given you any box unless and until you open it, then only you come.
Exactly. That is the Schrodinger cat experiment. So you have a cat in your box and you don't know whether it died or alive until you open the box. So, but there is information already. So if you will try to understand this, it's crazy. You cannot even get it. How it happened. So that's why I explained. Nobody understands the quantum, how it does. But we calculate and we get results. That's a shut up and calculate. Okay.
But as a teacher, we can't do like that.
Actually, the Oppenheimer, Richard Feynman, it's a something called Copenhagen interpretation. You Google it. You write in Google Copenhagen interpretation of quantum mechanics. It's shut up and calculate. So most renowned physicists, Nobel laureates ever happened in our scientific community, they told that quantum mechanics is what? Shut up and calculate. So that is the quantum mechanics. So you can tell students there is no harm. So well established term. Okay. So any other doubts in this? So you understand, ma'am, right? Information is traveled faster than speed of light due to the entanglement. But if you want to know, you need a classical message. So by knowing, you are bound, but information was not bound. It traveled faster than speed of light. So information violated, but we still abide by the rule established by Einstein. Assumption, no, it happened. Because of entanglement, real time, simultaneously it traveled from one galaxy to another galaxy. But you will never get until speed of light thing you abide. I hope this is clear, because this is most misunderstood part of quantum teleportation. So next I will go to other thing, how to generate. So SPDC is not only one way. There are other ways like some laser driven entangled state, ion trap, superconducting, multiple place way you can do that. So that's the advanced methods. Now application of teleportation and superdense coding, I already explained. So you can do some entanglement swapping, quantum networks, internet, these things you can do. So these are the applications. So these are the quantum storage system. So now I will explain the other part. So you did entanglement swapping, but entanglement swapping can be only done until you have a device which stores quantum information. If it doesn't store, it doesn't hold, you cannot get something out of it. So the second part comes. So till now I have completed one section. I will show you quickly the setup. And there is another thing which is called AFC. So EIT and AFC, there are two protocols. By using, you can create a memory. So one memory we have used, which we have developed, which is rubidium based. So rubidium, there is a atom, there is element, which rubidium vapor we have used inside our system. A vapor, we procured a vapor cell, and inside it quantum information can be stored. And something called erbium doped or rare earth ion doped material as well can store quantum information. So this is atomic frequency COM, where you can use rare earth ion doped materials. By using that, you can store quantum information out of it. So this is another part. So now I will go to our rare earths. So erbium, there is a erbium or praseodymium. There are multiple in periodic table. You see rare earth tables. So rare earth ion doped materials, by using that you can store quantum information. So these two. So atomic system like rubidium, cesium, they can be used, that are atomic vapor, and the rare earth ion doped material, they can be used. But our quantum memory is rubidium based, and which is room temperature. So this is our quantum memory, where rubidium, these are the energy levels of rubidium, and different light, they interact with that energy level, and they get a 3-level system. By using them, so think like this, You have an atom, so atom has energy levels, and a photon, they have also atomic property. So when atomic property meets with atomic property, then only they will interact. So atomic system we created, and photon which were entangled coming from somewhere, they will interact with that atomic system, a 3-level system, and they will get stored, and again they will be retrieved when we require. So by using them we can do entanglement swapping or quantum repeater or any sort of things. So these are the experimental setup. So this is a rubidium cell that kept in a chamber. So this is experimental setup in our lab. So we create qubits by using 2 different lasers, and we store them inside this rubidium vapor chamber, and we can retrieve it by using our signal, and whenever it will be required. So there is a very short span of time we can store, which is our quantum memory. So entanglement that we have generated, that can be stored inside this kind of system. So yeah, these are the results. So you see here, this x-axis is time, y-axis is the amplitude, and with time we have stored a signal, and this is the output that we have got by using this red laser. So red one is our control laser. So when to prepare atomic system, when to store qubit, when to read qubit, these sequence can be dictated by this control signal, and these are the results that has been stored and output. And these are old results. We have now very better results on storage in our lab, and so this is the major breakthrough. And we have developed a something called first quantum memory in India in our company, and second in the world. So there is no commercial quantum memory in whole world which is available, and we have developed first quantum memory in the world. So our team, we have developed that, and it's been used by IIT Madras. So IIT Madras, they are using that quantum memory right now for their quantum communication. So that's the one of achievement that we can say. And these are the products. So this is our lab experiment. These are our products that we are using it for academic. So for academic people, these are very important: EPS, source, and quantum memory. So you can generate entangled photon sources, you can store them, you can test inside the lab. So these are the products that we have made, and it's ready and people can procure it. So yeah.
No computing device is available.
So as I explained, computing is a different domain. So as Gopika was explaining in the morning, so computing, quantum computing, quantum communication, quantum sensing, and quantum materials, there are 4 verticals. So computing is being dealt with when you have a localized qubit, let's say a quantum computer, let's say 433 qubit quantum processor. So you can do a 433 qubit computation in that quantum computer, which in a fridge, it's written in a fridge, it's kept in a fridge, refrigerator. In your quantum computer, done, separate. Now come to the communication. So communication don't need 100 qubit or 1000 qubit quantum computer. It's not even required. You just have a source, you create entangled photon, you store inside a quantum memory, and you can do a communication. You can make a network out of it. So it's not required a quantum computer. What we have devised, we have made, that will be enough to develop a small scale network. That we have already proved, EPS QKD, that's a device we have made. So I hope your doubt has been answered, right? So this is the beauty, you don't need a quantum computer for doing quantum, right?
Equipment does not require computers.
Exactly. So it will come. So my next lecture is distributed quantum computing, which I'm delivering tomorrow. So in that, you need a quantum computer and quantum network both. So both will marry, and then distributed quantum computing will come. So that's the next thing I will discuss tomorrow. So these are the things are already we have made just for showcase. And this is some future thing that is our interest of research, our core research, where multiple devices will be connected just like our today's internet, and quantum repeater, quantum router, sources, and multiple QKD can be done. Whole world is working to achieve this. China is way ahead from us. US is way ahead from us, but we are still in the game. And by being developed India's first quantum memory, we have proved we have the potential to develop things. And we are working on this, and hopefully you will hear soon that Quantum AI Global made a first quantum network of the world.
You may be getting a Nobel Prize also.
Thank you. It's a big honor. So that's the all. And thank you so much to having me. And that's all. Any questions now? Overall, I'm done today. Anything related to the thing or outside as well. Because I also do multiple other studies as well, which relates. So quantum is very close to the spirituality. And it's
Quantum, I have a question.
Yeah.
Quantum internet, can you involve the classical computers also?
Sorry?
See, you cannot dispense these classical computers
Mm-hmm.
unless you take to this one. In your internet, quantum, can you integrate these two?
Yes, definitely. So it will be go hand to hand. As I explained, a teleportation, right? There was a quantum channel and there was a classical channel. So quantum channel and classical channel both work together to establish a system. So it's a misconception that quantum will replace classical. It's not. Both will work hand to hand. So it's like you have to walk, let's say, from campus to campus, right? You will use a cycle. You will not use a plane, right? To go to one faculty department to other, right? So quantum computer is like a plane, or quantum technology is like a plane, and this classical thing is like a bicycle. So, but you will use both. Depend on the requirement, right? So that's how it goes. So I hope.
Computers won't replace normal laptops, or we are using normal networks because it's not necessary. It is only useful for complex problems.
Exactly. That's why I said planes will not replace cycles.
Talking about quantum networks.
Yes. Sorry?
Security purpose for
Exactly. So let's say you are a defense person. Let's say China is going to attack India scenario, and there is a communication is happening in between India, and people were discussing, people were listening. US is listening. There is a geopolitical tension all over around. People are getting hack data and they're stealing data. What you will do in that case? If classical internet, everybody will hack and get information out of it. So you have to have something very secure, which cannot even broken by a quantum computer. So that's why quantum internet is required. All kind of large scale communications, highly confidential communications, strategic communications, where security is utmost important. These things can be done by quantum internet. I hope your question got answered. So anything else? Yeah. Sorry? So in computing, multiple electrons, ions, and trapped ions, NV centers, as I explained, multiple varieties of materials that are used. But the advantage with photons, they travel very fast, like speed of light, as I will know. So for communication, this is the best. And they do not interact. Photons never interact with other things. So they get absorbed and die, but they will not interact. But electrons, they will interact, they will produce electricity. Right? So that is the advantage of photons, right? So photons are extraordinary. That's why they are used for communication. but for computing, lots of varieties of materials. Yes, ma'am, you had some question. Yeah, you can ask.
That follows entanglement in the nature.
Physical
The example that follows entanglement.
entanglement. Okay. So first of all, so these are things about subatomic particles or photons. So whether we have observed entanglement or not, yes, we have observed in our lab. As I explained, we have Bell state measurement, Bell state preparation, we have everything. We have done that. We do daily basis. We observe that. And based on the mathematics, we can say we have entanglement. But observing these effects in real life, because there is no classical analog and we all are classical people. So you cannot, so we are three-dimensional classical entities. And we produce a average effect of subatomic particles interactions. So if you want to get teleport, you have to convert into energy. Right? Exactly. No, I'm telling you entanglement as well. So observe, there will be effect will be visible, right? Let's say the air is here, but we cannot see that with our bare eyes, but we can feel it. So similar mathematical results, experimental results will tell you, yes, that is entanglement, but you cannot directly see. Even means that's the limitations of humans or our entities. Maybe someday we can do that as well. Yeah, so something is beyond science and present science cannot explain things, and we are still evolving, we know very little. So but things are there way advanced than that, so we are still tending to that entity. So there are lots of things. Okay, so all right, thank you so much. Thanks for having me.
Thank you so much, sir, for your wonderful session and patient answering all our questions.
Yeah, thank you.
Please don't forget to attend the quiz tomorrow. And have a great
ఇంకా చాలా మంది రిజిస్టర్ అవ్వలేదు ఎందుకంటే సార్ మీరు